Hello everyone, my name is Vitor. I'm a PhD student at the University of Mons in Belgium, and I'm going to discuss about the idea of high-level synthesis and code design using Python. Over the past decades, huge effort has been deployed to increase the speed and throughput, as well as to decrease the latency of communication and data processing. This is particularly critical for real-time applications such as slow motion, 3D cameras, or autonomous vehicles. One of the technological answers to this issue is the hardware acceleration, which consists of using circuits instead of pure software to speed up the processing. A well-known example is to use the FPGA to get at the CPU or a GPU, but unfortunately, hardware acceleration is not easily accessible to software developers. It requires skills in hardware description languages such as Verilog or VHDL, which have a design flow and constraints quite different from other programming languages. In addition, the development of digital circuits has a longer time to market compared to pure software. Fortunately, two facts have been started to mitigate these issues. The adoption of FPGAs with a short time to market compared to the ASICs, and the rise of the higher level synthesis, HLS, which consists of coding a more usual higher level programming language that would later be used to generate the HDL, the hardware description language, or the HDL. In this work, we promote the idea to go further in the concept of high-level synthesis and code design, using the Python programming language. We believe that making hardware and software designs work closer will fasten the production and generate innovation. We propose three strategies to execute the Python code directly on the FPGA and discuss the advantages and drawbacks of each of them. The first proposed strategy is the direct execution of the Python bytecode by creating an architecture capable of decoding Python inside the FPGA. This would considerably reduce the execution time even compared to just-in-time solutions, since the application would run like a standalone binary without the need for operating system. And there will be no need for an extra layer of translation for the Python to native binary code. The drawbacks of this solution is that all the built-in functions have to be implemented in the architecture. For the pure Python code, this is feasible. The problem arrives when you try to include the external libraries that use C bindings. In order to be able to execute these libraries, we will need to implement all the external functions in the architecture, which might be a problem. Finally, the speed of the software development is much higher than the hardware, and catching up with that will be a big challenge. Another strategy is to accelerate only the most common functions in the hardware. This is commonly used with GPUs in libraries like TensorFlow and OpenCV that requires heavy computation in operations such as convolutions and matrix multiplications. The same idea could be applied for the FPGA, picking a widely used library such as NumPy and implementing the most common functions inside the FPGA. We can expect a modest speedup compared to the GPUs, since they also have special hardware for this kind of operation, but with a different mindset. The downside is that it will be hard to compete with them in scale, since implementing the same hardware would take a lot more space in the FPGA, and it cannot reach the same clock frequency. Besides that, GPUs can also switch kernels faster than we could reprogram the FPGAs. The last approach is to write a transpiler from Python code to some hardware description language, like Verilog or VHDL. By identifying patterns in the code that could be written in FPGA, we can reduce the execution times for some part of the code. The disadvantage is that writing a good transpiler is a challenge, since we need to identify patterns that are worth inputting in the FPGA, considering a lot of variables such as the data transmission time. Another difficulty is to ensure that the new bit strings are not needed to be created on the fly, in circumstances that requires recompilation, such as change the array shape in a function. Python is a powerful higher-level language with a rich ecosystem of APIs, ranging from scientific computation to artificial intelligence. It offers a natural way to gather software and hardware developments in the design of the core low-level optimized libraries. There are several possibilities to implement Python functions on the FPGA to offer a higher-level synthesis. Each strategy, as shown before, has its advantages and drawbacks. and the choice depends on the project's restrictions. For instance, the strategy of implementation of the Python bytecode processors can yield speedup as high as 200 times, as seen in some work, but it can be very time-consuming and complex to implement, compared to the hybrid strategies of implementing the most common functions that are much more straightforward, but they can't reach the same speedups. Thank you.